For part 3 of our little look at all things forces, I wanted to take a look at centripetal force. Centripetal force usually would be included in a review on circular motion as well as rotational systems, but it's a force, and we're talking about forces, so let's go ahead and let's talk about this force. Centripetal force is the net force acting on an object that causes it to go in a circle. So objects undergoing circular motion must have the force towards the center of the circle. If we have this object M right here, and at this exact moment, well, it's not drawn, if it has a velocity along that green arrow, which would be its tangential velocity, then if it wants to go in a circle, it has to stop going along that direction, it has to turn to the left. So at this instant, it needs to be nudged to the left in order to follow a new path that will allow it to be further along the circle. And then once it's on that new position, it needs to again be pushed to the left and to the left and to the left, and at every moment that's going around, to the left of it is the center of the circle. So centripetal forces are always directed towards the center of the circle because the acceleration, the change in velocity, has a direction towards the center of the circle. So if we take a look at the idea of a changing velocity, in this case it's the direction rather than the size of the velocity that is changing, it's still an acceleration, and accelerations require net forces. In this case, we call it the centripetal acceleration because I always think of it as centripetal, center pointing, makes sense to me. It's calculated as v squared over r, which, if you recall, we discussed that that comes from calculus and you do not need to prove it. It's a whole bunch of polar coordinates and derivatives and things. But what's important to know is that if we have the only force that's acting on an object happens to make it go in a circle, we call that net force the centripetal force. So we take m times a, but a is v squared over r, so the centripetal force is m times v squared over r. We can also calculate this using omegas and whatnot for circular motion when we do rotational systems, but that'll come later. For today, it's mv squared over r is the centripetal force. But again, let's reinforce this idea. This is the net force on the object. That net force can come from a car going around a curve and friction is providing it. It can be a planet going around a star, which we approximate as circular. And then the gravitational force is doing it. It could be a yo-yo being swung around on a string. And then for tension is providing the net force, which causes it to go in a circle. So it is the centripetal force. So that's a quick overview of the idea. Let's go ahead and take a look at something that's a little more complicated. A car going around a roller coaster loop. Let's say we have a 400 kilogram car, whatever you want to call it, and it's moving through a looped track as shown. Calculate the centripetal force at each marked location. Now, in this case, I've put some velocities here. Let's not worry necessarily if it's the actual velocity it would have based upon conservation of energy. Let's just stick with the numbers that are there. All I want to do is figure out what is the centripetal force acting on it. We're not worried about the normal force or any other forces. Let's pretend there's no air resistance. We just want to calculate what the centripetal force is at each of these 3 points. What is the net force on the cart? I want you to go ahead and try that out using our equation, see what you get, and we'll check our answers here in like, I don't know, 5 seconds. All right, there are my answers. Are your answers the same? I hope so. Maybe you even went back and took a look at the idea of conservation of energy that I kind of mumbled about and checked, and yeah, sure enough, that is what the velocity would be at the top. So you didn't need to worry about that though. So those are the centripetal forces that are acting on it. Now just to quickly check here, you can kind of skip forward if you don't want to do this, but in terms of units, forces are supposed to be newtons, which are kilogram meters per second squared. Units here, I've got kilograms, I've got meters over seconds squared over meters. So I'd end up with kilograms times meters squared over seconds squared over meters, and then one of those meters cancels. So yeah, that's newtons, kilograms, meters per second squared. So we got a whole lot of centripetal force required to make the cart go up in a circular path when it's down here, going pretty fast. Now when it gets higher up, it's not going as fast. It's going a third the velocity, so that would be 1/9 the overall centripetal force required because of the squared factor on the velocity. So it doesn't require as much force to make it go in a circle because it's going a lot slower. The faster you go, the harder it is to make something stay in a circular path. In this case, the force that is causing it to go in a circular path is going to be a combination of two things. Gravity, which is always acting straight down, and the track providing a normal force. Now at points A and C, that gravitational force is directly affecting what the normal force is because it's either going with or against the direction of the normal force. But in part B, the normal force is the only thing that's providing a centripetal force. Gravity is just trying to slow it down, which it is doing. It's slowing it down from 22 to 0.5 to eventually 10. But let's go and take a look at that problem. What if we wanted to figure out what the normal force was for the car at these three different points? We already know what the net force is, what the centripetal force acting on it is. Let's take a look at a setup for the normal force, the support force from the track at those 3 points. Now, I have deleted a lot of the the extra parts of the diagram just so that it's a circle. Let's go ahead and draw out what forces are acting on the object at those points. I'm going to draw force of gravity in green because gravity starts with a G. So I'll have M times G here for point A. For point B, M times G would be there, and for point C, M times G would be like so. So it's the same force factor, same direction in all three times. It's always pointing down towards the Earth. Apologize if it's a little crooked. Now I want to draw in which way the normal force should be going. And for normal, I'll go and draw it in blue. If we're down at the bottom of the track here, point A, the normal force should be straight up. At point B, the normal force should be this direction, which I apologize, it seems the center of the circle disappeared right there. And then at point C, the normal force would be like so. So the normal force is always pointing towards the center of the circle here. Now if there's no gravity, then the normal force would be the force that causes circular motion. There's nothing else pointing towards the center of the circle to make the car turn. So if this were in a track in outer space, really far away from all planets, and mg was negligible or non-existent, then if the cart was going around, the only thing that would cause a circular motion is the normal force in the track. So that makes sense. Gravity's just going to mess around with our balance. Now in all of these cases, the centripetal force is pointed towards the center. And that again is the net force. So we need to write out an equation for the net force of the object only involving forces that are along the radius. Call those radial forces. Only the forces that are directed along the direction of the radius do we care about. So in point A, normal force and weight are both important. They're either pushing towards the center of the circle or pulling away from it. At point B, it's only normal force. And in point C, again, normal force and weight are pointing, either trying to pull towards the center of the circle or away. In this case, they're both towards the center of the circle. So let's write those equations. Now, we've done this before. We did this when we first talked about circular motion, but let's go ahead and write it out again. For point A, we would say that the net force is going to be equal to, let's go up minus down, or let's go ahead and say towards the center of the circle is positive and away from it is negative. So towards the center of the circle, we've got normal force, away from it, subtract it, we got mg, and all that should be equal to the centripetal force. The centripetal force is towards the center of the circle, so it's going to be positive here. For point B, the only thing that we have is the normal force. The weight force is not along the direction of the radius, it's tangent to it, so it doesn't matter. So we'd have normal force is equal to centripetal force. And then for point C, we'd have towards the center of the circle normal force and weight force combined are producing that centripetal force. So we have a situation where gravity is working against the normal force. So in order to get the centripetal force, your normal force needs to be really big. The normal force here needs to prevent the object from getting pulled down from gravity and then still have enough to produce that centripetal force. So it's got to be a big number. Down for point C, the normal force, well, we got a centripetal force that's required, but the normal force only needs to contribute some of the factor. Weight is doing some of it for us already. So the weight force here in this case is going to produce some of the centripetal force, and then the normal force is going to pick up the slack. Now there's an interesting thing that we're going to see happen here when we kind of solve this out, but the normal force can actually drop to 0 if the only force required to make it go in a circle is whatever mg happens to be. In this particular case, because of the numbers that I chose, we're going to run into a little bit of a problem, but that'll bring up a good talking point. But this is the setup. So if we want to figure out what the normal force was at each of these points, we need to know what mg is and what fc is, and it just so happens that we already calculated what fc is for all of these. It was 18,000 newtons here, it was 2,000 newtons here, and it was something in between. I think it was 101.25, yeah, 101.25 right here. So we can calculate all those and see what we get. Why don't you give that a shot? We'll see what comes up with the problem here for part C. I'm going to go ahead and pause it, do the work. Alright, and here are the solutions. So solving for Fn in both these two equations for A and C, we would get a normal force required of 21,920 newtons. That is a lot. Okay, this thing has a mass, cart has a mass of 400 kilograms. That was from the previous example that we did. We're looking at like 5 times its weight in normal force. That means this track has to be really, really strong so it doesn't break. For point B, it's just going to be whatever the centripetal force was there. That's providing everything. But we run into the problem here. For point C, we're getting a negative force. That means the normal force wouldn't be in this. It would have to be pushing the other way, like gluing it down. So we run into the problem here of negative normal force. That can't happen. Right? That's impossible. So the question becomes, you can't have negative normal force. What did our car do? At some point here, the track was exerting a force of 21,900. That's 22,000 newtons. Here, the force dropped to 10,000. So at some point along the path, it got to the point where the force of gravity was stronger than whatever force was required to make it go in a circle. Which would mean that instead of following a path like this, and then going dot, 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 dot up to the top of the circle, our little car, unfortunately, has gone up and then it's become a projectile and it's fallen down. At some point here, gravity won and threw it into free fall, which was bad. That's bad. Don't want that to happen. Lost contact, which led it to go into free fall, which is why tracks on roller coasters and things generally have some sort of, some sort of contact that prevents them from falling off, because you might slow down because various reasons they want to keep you on that track. But if you're dealing with a little cart on just a flat surface, it'll stop connecting and move out of the way. So as soon as normal force, in this case, goes negative, we run into some problems. Now you can figure out the minimum force required for normal force is the minimum speed you can go is whatever velocity it takes so that centripetal force is equal to just weight. And at that point, whatever velocity that gives you, that would be a normal force of 0. So the track's not even doing anything for you. But you tend to coast past, and then the track has to push you so you don't go through a larger parabola. Okay, that's what I've got for some circular review. That ends part 3, and we'll go on to something else next.